Okay, so quiz 6 should be available for Canvas submission. Now, those of you that were part of the in-person session on Friday, you don't need to do this. I've got your pencil and paper work that I will grade and post to the Canvas gradebook. Okay, if you weren't part of the in-person session on Friday, then you need to submit a PDF through Canvas. Okay, so the key ideas for today are finishing up the multiplication algorithm. Friday, we actually talked quite a bit about the chip model. We'll need to make sure we understand how place value works and the role that the distributive property is playing in the multiplication algorithm. It's in the background, okay, so it's in there. And we're also going to do some more mental math, in particular, the importance of memorizing your squares. All right, so let's start out with a little review. And let me say this. Let's say I wanted to illustrate oh, 23 times 4. Maybe I'll even write it like this, 23 times 4 using the chip model. Okay, so somebody help me out here. How do I start?
Make a tens tray and a ones tray.
Okay, so I'll start out by making my trays. I'll need a tens tray, I'll need a ones tray. Okay, great, so I've got those. Now what do I do?
Four rows of 2 in the tens, and then 4 rows of 3 in the ones.
Okay, great. So I'm doing 4 rows. So this number on the bottom tells me how many copies of 23 I need to put into this model. And if we're putting 23 in the chip model, that would mean 2 tens chips.
Here for a second, so I can talk to both of you.
1, 2, 1, 2, 3. 1, 2, 1, 2, 3. 1, 2, 1, 2, 3.
You all need to go anyways until the earliest Saturday.
Okay,
That's
Madeline,
getting no more
I'll need
snow.
you to mute yourself.
But there's 2 more rounds coming starting tomorrow and Wednesday, and we could potentially another 11 inches down here. So if anybody calls and like, hey Maddie, we'll come pick you up, and there
Okay.
are cars and ditches stuck everywhere.
Oh.
Snow drift out the doors to here.
Okay, come on. Can I just mute that? Okay, great. All right. So, so 1, 2, 3, 4 copies of 23. Okay. And what next? Is this okay as it is now?
No, there's too many.
Right. I have 2. Go ahead.
There's too many in the ones place.
Right. I have too many in the ones place. Okay. Remember, the model is supposed to kind of give us the answer, right? Well, right now that it's saying we have 80, 12. All right. That's okay for a start, but what we need to do is we need to trade in 10 of these for a new chip in the tens place. And now we've got the place value working appropriately. You can't have any more than 10 in a single place. Okay, so 92. 2, we bring an additional 1 over, and that's how we get the 9. Okay, so 4 times 2 gives us 8, plus the additional 1 that we had from rebundling gives us a total of 9 chips in the tens place, 92. Okay, so this is something that I would expect you to be able to demonstrate on a quiz or test. All right, so be able to do that. Now, when we're doing the chip model, this number will probably be small. Okay, so 23 times 12, I guess we could do it in the chip model, but it would be quite tedious. Why would 23 times 12 be tedious in the chip model? What's the problem? What would the problem be?
12 is 2 digits.
Yeah, it's 2 digits, so how many rows of 23 would I have to do?
12.
I have to do 12 rows of 23, okay? And that would take a while to write down, and it wouldn't be all that clear. The point of the chip model is to make clear where this 1 is coming from. Okay, this 1 is coming from a regrouping. We're taking 10 of these and making 1 additional chip in the tens tray. Okay, so keep that in mind. And also note there's kind of a distributive property happening in the background. Okay. When I started here, before I did the regrouping, I said, all right, we have 8 and 12. So we have 80, 12. In a way, that's not really wrong, right? If I were to do 4 times 23, 4 times 20 plus 3, 4 times 20 is 80. 4 times 3 is 12. 80 plus 12 is 92. Okay, so that distributive property, multiplication distributing over addition, that's working right here. Okay, you can also see it in the chip model. We had 1, 2, 3, 4 copies of 20. That's 80. And then we had the additional 1 coming from over here. Okay, so you have multiple ways to understand where this 1 is coming from in the standard pencil and paper algorithm. Okay, now on Friday, we talked about several different stages of learning the multiplication algorithm. Remind me of what stage we left off with, please.
Five.
Okay, and what was the title of that? It was
Double grouping.
right, double regrouping. Okay, so stage 5 was double regrouping. We had an example kind of like this. This might not have been the exact problem I worked, but if you did, let's say, 55 times 3, okay, that's going to have too many 5s. Let me do something different. 44 would work. Okay, 44 times 3. Okay, the idea is that if I were to do the chip model for this, 1, 2, 3, 4, 1, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So I've got 3 copies of 44 loaded in. And here what I've got to do is I can take 10 of these from here, bring over 1, and then 10 of these from here and bring over 1. So double regrouping just means you have to regroup twice. And let's look at what we end up with. We end up with 2 there, 3 here, and 1. Okay, 132. And let's look at the standard algorithm. 3 times 4 is 12. You carry the 1. 3 times 4 is 12 plus 1 is 3. Notice what we have here. And then we have this additional 1 here. Okay, 3 times 4 is 12 plus 1 is 13. So this 1 is coming from being brought over here, and it gets added to the total that's going in the tens place. And this 1 comes from my rebundle. Okay. Now, if you notice all the stages that we had on Friday, all the stages had something in common. There was something similar about all the problems, in spite of different levels of difficulty with regrouping. So what was the common theme with all the problems on Friday?
Multiplying by a single digit.
Right, we had a single digit down at the bottom. And we even had one in this example. Of course, the multiplication algorithm is used to multiply any two numbers, not just something times a single digit number. So we have to make that transition as well. Now, that transition happens a bit later. Okay, that happens, depends on the school system, 3rd, 4th, 5th grade type of grade level that we're talking about. And let me go back to the document camera. Okay, so the transition starts with stuff like this. Okay, so stage 6. So 2-digit multipliers. But what you need to start with is stuff like this. Something like 12 times 40. Now you don't really need to know anything beyond this, okay? You just need to know 12 times 4, okay? And the idea is, well, if you're hitting it with a multiple of 10, that just adds an extra 0. Okay. So this first stage of 2-digit multipliers will just be building on to the 1-digit multipliers that we can already do. And the idea is, well, you're just leaving the ones tray empty. Okay. And then what you do is you work this kind of combined. So 2-digit multipliers part 1. And then 2-digit multipliers part 2. So what shall I do here? Let's do something like this. 24 times 13. Okay. Now, what we're going to do is we're just kind of doing the 2 steps together. Okay, so 24 times 3. And we can do that using the stuff that we've already discussed. Okay, but it's pretty easy. Of course, 24 times 3 would be 72. So that's what I would have down there. I guess if I was being really complete, right, 4 times 3 is 12. We'd carry a 1. 2 times 3 is 6. Add the 1, you get a 7. Okay, so that's where that's coming from. So that's 24 times 3. And now down here, I would have 240. And that's, of course, coming from 24 times 10. Okay, so I'm doing a single digit, and then I'm doing this business right here. And now, of course, we just add down 2, 1, carry the 1, 3, 312. Okay, so that would be the last stage in working the multiplication algorithm. Okay, so we used the chip model a lot when we were dealing with this algorithm, but we had a couple of different models that were useful for multiplication. The chip model is kind of coming from the set model, right? Like when we started out doing 3 times 5, we were doing 3 groups of 5. So you would take 5 items and put 1, 2, 3 groups where each group contained 5 items. That's kind of what we're doing in the chip model. It's just that you're dealing with a number that has something in the tens place and something in the ones place. So we kind of haven't talked about this rectangular array model that we had for multiplication. So let's show how that can be used as an alternative to understanding why the multiplication algorithm works. Okay, let's do a quick example here. Let's say I wanted to do 34 times 2. Okay, fairly simple one. We could do this in the chip model very easily. But here's how I might do it in the rectangular array model. Okay, so this is representing 30, 3 groups of 10. And down here, this is representing 4. Okay, so we'll do a little transition here. If I have, now you could, I wouldn't recommend you try to draw this, but imagine that I had 30 rows. Okay, we could certainly do that, but drawing it would be tedious. So let's just do, each of these blocks counts as 10 and this counts as 1. Okay, so this represents 30, this represents 4. Okay, so in fact, let's make the picture a little clearer like this. That's 30, that's 4 from 34. This side is 2, okay? 30 times 2, 60, okay? That's how many blocks we would have there if we had written them out. And here we'd have 8. Okay, so what you're doing is you're just going to combine this. You have 60 there, you have 8 there for 68. Okay, and you can do this with 2-digit numbers as well, 2-digit multipliers. Let's try this example. So this is example 1 up here. Example 2. 54 times 13. Let's do the rectangular model for this. Okay, so 54, 13. Okay. This side's 50, that's 4. 50 and 4. Okay. So what should I put here in this block? Right? Why?
500.
Yeah, 500, right? Because think about why this was a 60. It's 30 times 2. 30 times 2 is 60. So this block should be 50 times 10. 500. How about here?
150.
150, right? 50 times 3. This would be 40, and this would be 12. Okay, now what we would do is we would total all these out. Okay, so we'd have the 12, we'd have 150. Okay, we would have the 40, and then we would have the 500. And then we can add these columns here. So 2, I end up with a 0 there because 6, 10, I got to carry a 1 here. So 702. Okay, now you might say, well, why do we have all this extra stuff, right? But this, if we were to do the standard algorithm, 3 times 4 is 12, carry the 2, that's 162. It's just kind of an expanded version of what we had before. The 540 is coming from 10 times 54. Okay, and when we total these out, we get the same thing. This is just kind of exploding it a little bit. And the nice thing is that each of these blocks is coming from a single digit multiplication problem. Okay, to do 3 times 50, you don't need to work with 2-digit numbers, you just need to do 3 times 5 and tack on that extra 0 coming from the place value properties. Okay. So the rectangular array model gives us an alternative to the chip model. And the good thing about it is the rectangular array model can be used with 2-digit stuff. Another neat thing and this is something that extends to algebra, is the lattice method for multiplication. So help me out here. Pick an example for me. Give me a 3-digit number. Just make one up. Give me any 3-digit number.
782.
Okay, 782. Now give me a 2-digit number down here for my multiplier.
12.
12. Okay, 782 times 12. Okay, so to do the lattice method, here's what we're going to do. We're going to make a little grid. Okay, so 7, 8, 2, 1, 2. Okay, pretty easy to understand where those came from. Those are across the top. We're putting this one down the side. I want you to cut each of these squares in half. All right. Now I'm going to put some numbers in these little boxes. Okay. Where do you think this is coming from? 1, 6.
When you multiply 8 and 2.
Right. 8 times 2 is 16. So I put the tens place up here, and the ones place is down here. Okay. How come I didn't put anything up here?
It's a
Because
0.
Right. You could put a 0 there if you wanted to. So if you always wanted to put something in the tens place, you could put a 0 there. But since 2 times 4 doesn't have anything in the tens place, I tend to just leave it blank. Okay. Now we're going to fill out this row, and that's just going to be 7, 8, 2. Okay. Now, what we're going to do to finish off this multiplication problem is we are going to add along these diagonals. Okay, you notice how when we cut this in half, we created several diagonal strips. Okay, so, well, there's only one thing here, so that's a 4. Add these diagonally, you get an 8. Add these diagonally, you get a 13, so you got to do some carrying there, because each of the diagonals is going to be a place value. Okay, so I can't have 13 in this place value. I need to bring 1 over here and a 9. Okay, so the lattice multiplication algorithm is telling me this should be 9, 3, 8, 4. Okay, so let's kind of compare that to the standard algorithm here. You have a 4, 6, carry the 1, 14, that's 15, 0, 2, 8, 7, 4, 8, 13, carry the 1, 9. Okay, so notice exactly what we had right here, right? The ones digit, just a 4. The tens, 2 plus 6, that's how we got that. The hundreds digit, 8 and 5. Well, there's our 5 right there. 4 plus 1 is 5. Okay, and then for the thousands digit, we're carrying the 1, just like we did right here. 1 plus 1 is 2, plus 7 is 9. Okay, so lattice multiplication. Make a grid. Put each multiplier around the perimeter, and then we fill in the little boxes. Okay, so note just a couple of additional items here. For example, that's from the tens, and that's from the ones. Okay, so lattice multiplication. It extends to algebra, which is why I like it. We'll see that a little bit later in the course. Okay. I do want to get back to doing some mental math. I want to kind of build on what we already know. Let's do a couple of warm-up problems. Ooh. Try that one. Oh, and oh, how about this? Okay, so a couple of warm-up mental math problems. Somebody help me out with this first one. 37 plus 23.
You would bring the 3 over.
Okay, right. We do a technique called compensation. We notice, okay, this is close to being a multiple of 10. We need 3 extra, so we bring 3 over. And this is what we're thinking. So our thinking is if I bring the 3 over, this is 40 plus 20, 60. Okay, so we took a 2-digit problem, made it a 1-digit problem. All we need to know is 4 plus 2. Okay. What's the process that would help us out here with this next one? 64 minus 19.
Think of it as 64 minus 20 and add the 1 back.
Okay, right. So the compensation for subtraction is a little bit different. You need to focus on this part right here. You want to make the thing you're subtracting to be a multiple of 10. So rather than subtract 20, rather than subtracting 19, subtract 20, which is easy. That's 44. Then throw 1 back to get 45. Okay, this is a multiplication problem, multiplying by 5. So help me out, help me remember what the process was. There was a very easy way to do it.
Multiply by 10, divide by 2.
Okay, right, so multiply by 10, divide by 2. In this case, it might actually be even better to do it in the other order. Divide by 2, multiply by 10, because this is even right here. So if I divide this by 2, I get 12. Multiply by 10 is, of course, 120. I probably didn't even need to write that there. How about this? How about dividing by 5?
Double and divide by 10.
Right, double this. So what if I double 160? What do I get?
320.
320, and then I take that, divide by 10. And the point being, dividing by 10 is easy. This is a multiple of 10. If I divide that by 10, I would just get rid of the zeros. Okay, remember, multiplication and division are inverses of each other. So multiplying by 10, that's easy. You add a 0. Divide by 10, you do the opposite of that. Divide by 10, you take off a 0. Okay, so that's a little review here. Now, the new thing I want to add to our mental math repertoire is the idea of squares. Okay. Okay, so I call these numbers squares. Okay, it's not just me, it's sort of a common term. So why is this called a square? Why is 9 a square?
It's 3 squared.
Right, 3 squared, which of course is 3 times 3. Okay, so this is 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9, and of course 10 times 10. Okay. Here are some additional squares that I would like you to remember. 11 squared. Okay, 11 squared is 121. 12 squared is 144. 13 squared, 169. 14 squared, 196. 15 squared, 225. And finally, 16 squared is 256. Okay. So these down here, you probably know already. If you don't, just make sure you kind of commit them to your memory as the squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. Add these to your arsenal as well. 11 squared, 121, 12 squared, 144, 13 squared, 169, 14 squared, 196, 15 squared, 225, 16 squared, 256. Okay, so these are things you just need to kind of know. And this allows us to build up our mental math to tackle problems that we wouldn't be able to without them, at least not as easily. Okay, so one of the things I want you to remember is the algorithms that we've discussed, the pencil and paper algorithms, they help us complete the topic and they always work. But that doesn't mean you need to use the algorithms all the time. Some folks get confused and think the standard pencil and paper algorithm is multiplication. And whenever you have a multiplication problem, you have to do the standard pencil and paper algorithm. So they end up doing wacky stuff like trying to do the standard pencil and paper algorithm when you're multiplying this by 30. There's no reason to do the standard pencil and paper algorithm in this case. Okay, it can be done much more quickly using our mental math techniques. So here are some problems where knowing these squares helps a lot. Okay. A problem like this, 13 times 14. Okay, well, here's how I would view it. 14 is one more than 13. Okay, so by the distributive property, this would be 13 times 13 plus 13 times 1. We know what 13 squared is because it's on our list of squares. It's 169. Okay. And 182. Okay, how did I get the 182 here from this line?
You added it.
Right, so it took 169 plus the 13. If you want to do that really quickly mentally, bring over a 1. This is 170 and 12. 170 plus 12, 182. Okay, I want you to try something similar. Take a moment and try this one. 15 times 16. Try to use what we know about squares. Now I know in this example, it was kind of overkill. I wouldn't ordinarily write this much. It was just, since it was our first time dealing with a problem like this, I wanted to show you my thinking. We could probably jump right to this or even this, because we got 14 copies of 13. We know if we have 13 copies, that gets us here to 169. Tack on that additional 1. Okay? So try a similar idea to find this problem. Take a minute or two to work on it. Okay. So what would be my starting point here? 15 times 16. Using what we now know about squares.
15 squared plus 15.
Okay, right, we would start out with 15 squared, and then we would add one additional copy of 15, right? Because 15 copies of 15 would get us here. We don't want 15 copies, we want 16, so we throw an additional one on. 15 squared we know is 225, and then we tack on 15. If you want, you move the 5 over, now you got 230, so you got 240. I suppose an alternative, we hadn't really talked about this, but we have talked about multiplying by 2, 4, 8. How do you multiply by 4 again?
Double twice.
You double twice. To multiply by 8, we would double 3 times. To multiply by 16, we would double 4 times. So you start with 15, double it, now you're at 30. Double it, you're at 60. Double it, you're at 120. Double it again, and you're at 240. Okay, so a couple of ways to get this problem done. Okay, let me see if there were any other problems I wanted to discuss. Oh, okay. Let's throw in one like this. Okay, this does not fit the pattern of the previous two, right? The pattern of the previous two is we had a number and then something one bigger. So we took the square and then tacked on one more. Here's how I would tackle a problem like this. Okay. There's a couple of ways to think about it. There's a couple of ways to think about 22. I'm thinking about it this way for this problem. Okay, so instead of viewing this as just a 22, I got 10 and then 12 more. Okay, use the distributive property, 12 times 10 and 12 times 12. We know what 12 squared is, it's 144, so 264. Okay, so that's another way squares can help us out here. You can use them in problems like this where you apply the distributive property. Okay, so memorize that list of squares I gave you. 11, 12, 13, 14, 15, 16. Okay, know your squares up through 16. And be able to use those for mental math problems, in particular stuff like this. Okay, so let's talk about some homework here. Okay, I'm looking through elementary math for teachers. We're working on the multiplication algorithm. Okay, so if you have not already done so, read through pages 66 to 70 of elementary math for teachers. On page 70, I want your work on 1 through 6 and also do number 8. Problems 1 through 6 and number 8. Let me see if I have any notes here. No, okay, so go through that section and then we will start the division algorithm next time. Okay, now I just got, during class, I got a text from SWOSU Alert saying that we'll be doing virtual instruction on Tuesday as well. Okay, so obviously that doesn't affect us unless they call virtual instruction for Wednesday. So so keep an eye on that. If we're still virtual on Wednesday, I will post links to office hours and stuff like that. Okay, so any last minute questions? All right, so make sure you go on Canvas. For those of you that were not in person on Friday, go on Canvas, work out quiz 6. I'll extend the deadline here. Right now it says 11:30. Oh, okay, no, February 16th at midnight. Okay, so you've got till tomorrow, basically. Okay, or I guess that's noon. 12 p.m. is noon. Okay, so get quiz 6 uploaded by tomorrow morning. I'll grade them, and then I'll see you on Wednesday. Okay, unless somebody has something, I'm going to end the meeting. Okay. Bye.